Properties of continuous functions. If the functions f and g are continuous at x equal to c, then the following combinations are continuous at x equal to c. And look at this. This is very familiar. This is just the same as the properties of limits of a function, whether it exists or not. So if you have a sum, if I have two functions, okay, f and g, if f is continuous, g is continuous, that means their sum is continuous, their difference is continuous. Here, a constant times a function where the function is continuous makes constant multiples continuous. A product of two continuous functions are also continuous. A quotient of two continuous functions is also continuous, provided that we don't have a zero in the denominator. And a power of a function is also continuous, as well as the nth root of a function. Just to give you a few examples, if I have y equal to x squared plus 3x, this is a continuous function. Okay, it's powers of the identity function. Here it's a multiple, constant multiple of the identity function, and then the two together is the sum, and that makes it y equal to x squared plus 3x continuous. Okay, y is continuous everywhere. Okay, how about this one? Y is equal to sine x plus cosine x. Is that continuous everywhere? Okay, yes indeed, because sine x is continuous, cosine x is continuous, so their sum has to be continuous. So what are some common functions that are continuous? Okay, so far what we have been talking about are usually polynomials. Let's say y is equal to 3 x to the fourth plus 7x cubed minus 4x plus 7. Okay, that's a continuous function. Some trig functions are continuous. Some trigonometric functions are continuous. A few examples would be y is equal to sine of x, y is equal to cosine of x. What about y is equal to secant of x? Well, it will depend on the domain. So y equal to secant of x, cosine of x behaves this way: pi over 2, 3 pi over 2 up to 2 pi. Now if I take the reciprocal of when cosine of x is 0, then that's when it'll be undefined. So to graph secant, that's my secant of x. Well, it is conditional in the sense that it is continuous at certain intervals. Okay, so I will say it's continuous for all x not equal to any multiple of pi over 2 where n is an odd number, like pi over 2, 3 pi over 2, 5 pi over 2, minus pi over 2, etc. Other kinds of examples that I'm sure we'll be looking at is you will have the exponential functions and also the logarithmic functions. But we have to be careful about our log functions. We say it's continuous in its domain, okay? Because if I draw the graph of a log function, the domain is going to be from 0 to plus infinity. So as long as we're in this interior, the function is continuous. This is just a few of our common functions that are continuous. How about if we have a composition of functions? Well, what this diagram shows that if I have a continuous function f at c, so then that means it will have an f of c, that's the limit as x approaches c. And then I'll have another continuous function g, which is continuous at f of c. Then my composition will also be continuous. That's all that this says. Example, suppose f of x is sine of x. How do I know that g of x is the absolute value of x. Both of these are continuous, right? Okay. Remember that the graph, let's look at the graph of sine of x. Well, we just did it a while ago. And then the absolute value. And remember that it continues on. If I have g of f, what does that look like? I'm taking the absolute value of sine of x. Is this continuous? Question, is that continuous? Well, based on this diagram that I have here, that if I have a composition of two continuous functions, then the composition is also continuous. Even if I don't have to graph that, I know that the sine of x, the absolute value of sine of x is continuous. Well, I could graph it. What do you mean by the sine of absolute value of the sine of x? Well, here's my sine of x. Wherever it's negative, you just make it positive. So what you're actually going to see is right there. It's like a scallop. And so on and so forth. Okay. There you go. And notice there's no gap, there's no hole, there's no jump. And so we have that the absolute value of sine of x is continuous. Here is another example of a composition function, but just to show that the function y equal to, let me write that down. It's like this. Ooh, I need a red color to be more visible. Just to see how it looks like. Y is equal to the absolute value of x sine of x over x squared plus 2. Do we have any problem as far as having a 0 in the denominator? No, because x squared plus 2 will always be positive and non-zero. At the top, you have a continuous function times the identity function. They're continuous, okay? So the ratio of two continuous functions, as long as there's no 0 in the denominator, okay, that is continuous. And if you take the absolute value, then it's also continuous because the absolute value function is continuous.